Okay, good evening, everybody. My name is Andrew Stevenson. I'm the chair of the Teeside Panel of the Institution of Mechanical Engineers based in North East England. And I'm pleased to welcome you all to our second Tech Talk event. This one's the first we've held by webinar, so please bear with us if we have any IT niggles along the way. I'm delighted that we've had over 200 people sign up for tonight's event, with registrations as far afield as Australia, Japan and Norway. So thank you very much for joining us. So the format for tonight is two short 15-minute presentations, each followed by a brief Q&A session with each speaker. So you can submit some questions to me via the Q&A box on the WebEx screen, and I'll pass them on to the speaker at the end of their presentation. So our two speakers are Bowman Bradley, Chair of the North East Region, who will be talking about sustainable propulsion on inland waterways, and Djawad, Chair of the Young Members Panel on Teesside, who's going to be talking about Kite wind turbines. So before we start, the Teesside Panel would be very interested in any volunteers who would be interested in giving a short talk at a future event on any mechanical engineering based topic. So if you're interested, please get in touch with myself via the email address that's shown on the screen or through the IMechE's Near You website. So thanks for listening. We'll hand across to Bowman now, who's going to get the first talk underway. And if you have any technical questions, if you can submit them via the Q&A tab, we'll try and pass them on to Bowman at the end of his presentation. Thank you.
Good evening, everybody. I'm just going to try and get the slides up. That does seem to be working. Good evening, everybody. We'll see those slides. As said, I happen to be the chair of the North East region. More importantly, for tonight, I'm a member of something called the Inland Waterways Association. I'm doing this presentation on behalf of the Inland Waterways Sustainable Propulsion Group. We're a small group of members of the association who are looking at ways of making cruising the inland waterways in the future more sustainable and hopefully zero carbon, but certainly low carbon. Many people coming into this webinar tonight will probably know nothing about the Inland Waterways Association and probably very little at all. So I will move to just give you a little bit of background as to what we are and what we do. The Waterways Association was founded in 1946, and one of the founders was a guy called Tom Rolt, who wrote Oh, Rod, You're Right. Now, Tom Rolt was the book that launched the Inland Waterways Association. If you do during lockdown, I'd say you might like to have a read of it. Its purpose is in the second bullet point. I'll not read it out, but basically, the Inland Waterways Association prevented the closure of the British canal network after the war. And very successful in that regard. We have 16,000 members, and probably our most famous member is David Suchet, otherwise known as with the Inland Waterways Association Vice Presidents. So I've mentioned there the British Canal Network. As I say, many people may not know it even exists. Canals were started in England in, I think it was 1761. The canal appeared from then to really to around about the First World War. That is what the canal network looked like in around about 1830. And if you recollect, certainly the on the side will know that somebody in 1825 invented something else, which we call the railway. So after 1830, the canal network did start to decline to a certain extent. But if I now show you what the canal network looks like today, that is the canal network in 2020, the English and Welsh canal network. There are a few in Scotland, but they're slightly off the map. And as you see, it's not very, very different to the canal network in 1830. And it is now a wonderful leisure resource for the whole country. And there are in fact more boats on that registered on that network today than when the canals were a commercial proposition in the 18 and 1900s. So we need to think about how do we get boats around that canal network. There's the way it all started. And there are certain people who suggested that the Sustainable Propulsion Group that went on for quite a long time, until around about the turn of the 19th century, when something else came along. And that is a boat called President it was launched in 1909, and it's actually powered by a steam engine. And the interest in that's President the Queen's Jubilee pageant in 2012 on the Thames. I was taken by a friend of mine. You might have seen the coverage of this event on the television in 2012. The BBC didn't bother showing President. And there it is today, passing my boat on the middle of the Union Canal, pulling its butty. The butty is a boat without a boat this. And there's the engine, a single-cylinder steam engine, powered by coal. That's how we got rid of the hull. Moving on, there's a very similar-looking boat, a little bit later, probably around about 1924, powered by something else. Powered by that. Semi-diesel, single-cylinder. It's called a semi-diesel because it is a hot bulb. To start the engine, you have to fire a button, which is that thing there at the top of the engine. You've got to fire that up for 20 minutes to start the engine, and then you kick over this big flywheel and the engine starts. Quite a you stop the engine and start up in the opposite direction. But then somebody engine, such you might find in a boat like that today. So there we go. We've now got a diesel. We've got a diesel-powered narrowboat, and most of the narrowboats today are in fact powered by a diesel engine. That's my boat. It's powered by a diesel engine. 57 feet. It's 15 tons. There's its engine. It's a Isuzu simple 4-pot diesel engine. I use about 1.5 litres of diesel an hour when I'm cruising that boat. We'll see how relevant that is when we get down to the sustainability end. It's a very simple diesel engine. It's about 2 litres. So it's quite a big engine, really. Just to look like inside, just to make you jealous. There it is. That's my boat. But what about the future? Because petrols are going significantly out of fashion. So what are we going to do to make narrowboating a little more sustainable in the future? Now, this is not a technical talk. I'm not going to give you a lot of technical equations or formulae or anything like that. What we're trying to do here is to paint a vision of what narrowboating and propelling narrowboats and other river boats and canal boats might look like in the future. And it is a vision. It's based on technology which is available today, but has not been necessarily fully used on boats. So what about the future? We've actually got 3 problems in propelling boats around the canal system. First problem is, if we're going to build a new boat and we're not going to use a diesel engine, what are we going to use? And there's a number of options which we'll look at in a minute. We've also got an existing fleet of boats. There's about 20,000 on the waterways. The vast majority of them are powered by diesel. So they also last a long time. We'll talk about that again in a minute. We've also got to refuel and recharge those boats. Whatever method we use, somehow we've got to be able to refuel them. Whether we talk about battery-powered boats or whether, as we will do, talk about hydrogen-powered boats, we've got to be able to refuel them. At the moment, we refuel them with red diesel using a thing that you might expect, a simple device at the side of the canal which pumps diesel in. Are we going to be looking at charging points like that? Are we going to be looking at hydrogen refueling like that? So there's the option. There's the problem. So let's look at what the future narrowboat might look like. It's designed for flexibility because different people use their boats in different ways. Some people live on them and never. Some people cruise the whole of the time around the system, which is quite extensive, 2,500 to 3,000 miles of canals in that network I showed you. So some people are cruising all the time. Some people take their boats out the whole summer. Some people use it for a week or a fortnight. Some people live most of the time and maybe just take it up for the day. They all need different solutions. But we think that now an electric motor, that's almost certain. It will have a battery to drive that motor. But we need a means of charging that battery. We think it's going to be equipped with a hydrogen tank and a hydrogen fuel cell. These exist at the moment. We have other ways of charging the battery. You can connect it when you're in the marina, when you plug it into a shore connection. You can use onboard photovoltaic cells, or indeed the fuel cell will charge the battery. Everyone says hydrogen. Wow, that's dodgy. But California has got 10,000 plus hydrogen cars. They do exist, it can be done. All the technologies that we're playing here exist, and they're all being developed in other fields of transport. We'll see in a little while how that's coming along. It's been done before. The Ross Barlow is a canal boat driven by hydrogen. It was built in 2007 by Birmingham University. Now, in terms of development of alternative propulsion, 2007 is quite a long time ago. And the technology that was available in 2007 was very different from the technology today. But if you look at that, which is how the Ross Barlow is propelled, all the units of that exist in our narrowboat of the future. You've got a hydrogen storage. Today, you probably use pressurized hydrogen. This is a solid state system, a metal hydride system. We've come on quite a way since then, although that might be coming back. A 1 kilowatt fuel cell. That was probably the biggest you could get in 2007. As you'll see later, nowadays, they can drive trains. So that's come on quite a bit. They had a battery stack. They were lead acid batteries. We've got better versions of batteries now than that. A brushed motor, you wouldn't use that today. Everything's come on, everything's improved. But the basic system was very much the narrow we're now talking about. But let us look at how we get there. Because at the moment, we've got a lot of narrowboats powered by diesel engines. And just like with cars, you can a hybrid system. Now, this is a hybrid canal boat engine, which you can buy today. It is a 2-litre diesel engine, which is the engine that drives my boat. But you'll see on the back, there is a large motor generator bolted. That can be used either to shaft, which is sitting here, through a belt, or if the diesel engine is running, it can be used to charge the batteries. Now, as with cars, you can get a very significant, a slightly significant improvement in fuel consumption with a device like that. But we don't think that is the way forward because, quite frankly, it's not good enough. It doesn't give us the sort of improvements that we're looking for. But that is available today, the parallel hybrid. A better solution, we believe, something that is generally known as a serial hybrid. So what's a serial hybrid? Well, you've got to start with a propeller at the back of the boat. So there's a propeller. And one of the interesting things about propellers, certainly in canals, is that the bigger they are and the slower they turn, the more efficient they are in terms of how much fuel you need. So just let's leave that in the back of our minds for a minute. We need an electric motor. These have improved no end since Ross Barlow, mainly because they've been developed for road transport. And believe me, the power you need to drive a canal boat is well within the sort of powers that even the smallest motor car needs. You need a battery. Probably these days, if you can afford it, it'll be a lithium-ion battery. But one of the points about a narrowboat is that the weight and space are not a problem compared with a car. So you could very easily use less batteries even today. So now we've got to think about how we charge that battery. We can plug it into the and charge it up from what canal people and know as a hookup, which is typically a 16 amp power supply, a big bag, the power supply you have at home, and a 13 amp socket. And if your boat is sitting in the marina for a week and you only use weekends, that's going to be more than adequate. You can charge it up with PV. Another boat is quite good at putting PV cells. There's a lot of space in which you can put photovoltaics. So you can get a fair amount of power from PV cells on a canal boat. You won't get enough power to drive the boat. There is one boat around, the one you've seen a picture of, who do say you can drive the boat just off the PV cells. But I think they will need a very strong summer day. They will need the sun high in the sky. And I don't think they'll be able to run the center at the same time. So how do we charge the battery? Well, one way you can do it is with a generator. Now, you may say that's not a lot of good because that is still going to use diesel or petrol. It will typically use diesel. But that can be a very small generator because it's a very efficient system. The engine in my canal boat is about 20 kilowatts. It's about 40 horsepower. One of our members has exactly the configuration. The marine generator is 2.5 kilowatts. And that is enough. He can run his boat on 2.5 kilowatts because that marine generator can run 24 hours a day if he wanted. It drives a much bigger propeller than a diesel engine can do, so it's more efficient. He's running a marine at its design capacity rather than my big 2-litre diesel engine, which is probably barely doing more than tick over most of the time. So that is an inherently more efficient system than the one I have on my boat. And that system, even run by diesel, uses about 1/3 of the diesel that my 2-litre diesel engine uses. So that could be a significant step forward to sustainable propulsion. But it's got another advantage. It is fairly straightforward to do that. You can fairly easily replace the small generator with a hydrogen fuel cell. So there we have the narrowboat of the future. So we think the way forward to get there is the serial hybrid. Why do we need a step to get there? We'll come to that in a minute. So that we see as the narrowboat of the future. So what do we do about the existing fleet? There's really two arms to the existing fleet. There's boats like mine, which is shown up there on the right-hand side, and there's the more traditional boats. Both run on diesel. And boats, actually, that boat of mine is 15 years old. It's probably got at least another 30 years in it. So the existing fleet is not going to disappear anytime soon. So the existing fleet's going to be with us for a long time. So can we run it on 100% diesel? There's a possibility. Biodiesel is a lot more environmentally friendly. It is not 100% environmentally friendly, and it has some problems. Let's have a look at one. Problems with 100% biodiesel. It is put into ordinary road diesel at the moment at a percentage that I think at the moment somewhere between 5 and 10%. There are some engines, some diesel engines will run on 100% biodiesel. Some of the seals in their fuel systems won't resist Some engines, such as mine, will. The older engines, as on the boat below, probably won't. So they need modifications mainly to their fuel system to make them biodiesel resistant. Biodiesel actually burns quite slowly compared with mineral diesel. And that means that if you put 100% biodiesel in your turbocharged road car running at 4,500 RPM, most canal boat diesels do little more than tick over. I'll cruise miles to 11 RPM. I think it will run quite happily on biodiesel, whereas a road car probably would not. Biodiesel doesn't perform well at low ambient temperatures. If anyone's ever put olive oil in the fridge, it goes cloudy and semi-solid. Biodiesel is made from vegetable oils. Depending on the vegetable oil you use, at low winter temperatures in the UK, biodiesel goes solid, which is a bit of a problem if you're sitting in a marina over the winter. So you need to be very careful what you make your biodiesel from if you want to use it 100% in the UK. Also, biodiesel absorbs moisture more readily than mineral diesel. It is a problem with mineral diesel, and we put additives in our tanks when they're sitting over the winter to try and reduce that. We would have to be even more careful with biodiesel, but it's manageable. The big issue with biodiesel, to be honest, is sustainability. It's made from vegetable oil. Most of the vegetable oils that it's made from are in fact foodstuffs. So the most popular one is palm oil, which is a foodstuff. It can be made from many oils that you'll find in your kitchen. So if we were to use bio to power the whole of the lorry car fleet in the world, it would take away it from oil. And even if you can use a mineral oil or a vegetable oil, is not a foodstuff oil, it would still need to be grown on land that could otherwise be used for food, which is one of the reasons why I believe that biodiesel will never become the solution for road transport. But the Inland Waterways uses a relatively small amount of diesel. It uses about 5,000 tonnes a year. That's our best estimate at the moment. That's a lot if you put it in one place, but in the big picture world fuel supply, it's not massive. So maybe able to do. And improved biodiesel are being developed. The Sustainable Boating Group come across a biodiesel claims and appears to overcome most of the problems that I've listed above. We would have tested it by now with a lockdown in place. We've not been able to do it. But it does look like biodiesel might be the way forward for the existing fleet. So let's go and look at recharging and refueling. Because we talk about batteries, whether we talk about hydrogen, whether we talk about biodiesel, we've still got to recharge or refuel the boat. So the existing fleet, well, that's fairly straightforward. Biodiesel can use the existing refueling infrastructure. Pumps exist in marinas, boatyards, hire bases. They're scattered around the system. They can pump biodiesel. Maybe some modifications are needed for seals to resist 100% biodiesel, but electrical recharging. There's a high-powered recharge which you'll find motorway service stations today. Most marinas and home at that level of charging. If a boat's sitting in a marina for a week, yes, you could charge it up on your plug-in. But we don't think every marina or home mooring is going to have one of those big ones. Bankside charging station. You'd have to put these things alongside the canal. I rather suspect them for it. They're quite expensive, so I really can't see a high-powered charging system being available at every overnight mooring. And also, as we all know with cars, batteries take time to charge, and the range is not massive. These things are going to improve, but as at the moment, it's problematic. Hydrogen. Hydrogen has got an advantage. You can fill a hydrogen car or boat or any other vehicle in about the same time as you can fill a car with diesel or petrol. So it does away with that problem. You can fill hydrogen in a car to give you roughly equivalent range to the sort of vehicle you can used to. My narrowboat has a 40 gallon fuel tank, and it can run for about a month on that tank. You could do a single hydrogen, but rather like the electrical system, it requires a distribution infrastructure. You could imagine hydrogen regions in boatyards and boat bases, as we have for diesel at the moment. The units would be more expensive, but technology exists. But with both electrical recharging and hydrogen, you've got a chicken and egg situation. Nobody's going to buy an electric or a hydrogen boat until the infrastructure's there to charge them, refuel them, and nobody is going to install them until the boats are available. So there's a problem. We've got the same problem on the roads, I would suggest. Battery cars and hydrogen cars. So that's a problem we need to solve. So everyone says hydrogen, dangerous stuff. It explodes. Well, yes, hydrogen explodes in petrol. But as I think most engineers will know, hydrogen engineering is well understood. I believe you can engineer a hydrogen system to be as petrol system. Maybe not as intrinsically safe as a diesel system, but as safe as a petrol system. And things are happening. A few days ago, somebody suggested they'd found a way of storing hydrogen which didn't involve high pressure fuel tanks. That's got to be a plus. And Hyundai announced plans for a hydrogen-powered excavator. That was only roughly a month ago. So let's have a look at some hydrogen things that actually exist. That is a hydrogen-powered boat. It's a ferry boat. Now, I did say that there aren't many hydrogen filling stations around the Inland Waterways system. I was corrected the other day. There is one in Bristol Docks. I think it's the only one in the country. There's a hydrogen bus. I think there's going to be on the London roads in the next few months. Those exist, and they are going to go into service. There's a tractor unit in the States converted by Cummins to hydrogen. It can be done. There's a train being developed by Alstom at the moment for use on the British railways. That is in fact, an electric train. Still an electric train, which is a hydrogen fuel cell. So hydrogen, look, just for fun, there's something to start with, a hydrogen-powered forklift truck. So guys, that's a quick run through our vision for how sustainable boating might take place in the future. I'll just make a plug for the Inland Waterways Association. We were founded to preserve the British Canal network. We're still doing it. And I think by finding a way of propelling boats in an environmentally friendly manner, that is as important in preserving the British Canal network as the great leisure facility that it is. It's just as important as the work that the Inland Waterways did physically to preserve it in the 40s, 50s, 60s and 70s. So there we go. Any questions, guys?
Okay, thank you for that, Bowman. Yeah, we've got a few questions. The first one's from Alan Dixon, who asks, how does a future engine propulsion system size, so how does the size compare with existing systems as a percentage of hull size?
As a percentage of hull size, not sure I understand that. We have mainly focused our work on canal boats, narrow boats and broad beam boats. Both boats, they tend to be all the same sort of size. They're all 7 foot wide. They vary in length from 30 or 40 feet to 70 feet. My boat, which is 50 feet long, is probably the commonest size on the waterways. I have a 43 horsepower diesel engine, 2 litre diesel engine there, and my colleague who has a serial hybrid boat thinks that's what he doesn't think. He knows that he can run his boat on about between 2 and 4 kilowatts. depending on how he's going. Does that answer the question?
Yeah, I think I was just trying to get understanding on the scale of the equipment, how the kind of hydrogen system would compare with what's in place at the moment.
You mean in terms of physical size?
Yes.
I would say very, very similar, but more scattered, because at the moment, a big diesel lump in the back of my boat with a gearbox on the back, it's all sitting in one engine, you would expect. With the hybrid system that we envisage, the motor is relatively small. The battery, depending on what technology you use, if you use lead acid battery, quite big, but there's plenty of space inside the boat for those. The fuel cell is quite small, probably the size of a couple of large suitcases, maybe a bit smaller. The generator, if you're using a diesel generator, is a lot smaller than my diesel engine. A hydrogen fuel tank would probably be a bit bigger than my diesel tank. But one thing about narrowboats particularly, certainly compared with, say, cars, there's plenty of space. Space and weight are not a problem.
Okay, we've got another question asking about the differences in cost between existing diesel systems and a hydrogen system.
Darn good question. It depends who you talk to. A typical diesel setup, someone selling diesel engines is going to kill me for giving the wrong numbers. I would think a diesel setup today would be, if you just, before you install it, just to buy it off the shelf with its gearbox and various other bits and bobs, is going to be somewhere about £6,000. At the moment, hydrogen fuel cells are quite expensive. You're talking about £2,000 per kilowatt. So a 3 kilowatt fuel cell will cost you £6,000. You've then got to buy a battery, you've then got to buy a motor, you've then got to buy an electronic control system. So at the moment, you're looking at a system which maybe might cost twice what a diesel would cost. Having said that, and in mind we're talking new narrowboats, a narrowboat's not a cheap piece of kit. I mean, a boat like mine would probably cost brand new, between 100 and 120,000. So, extra 5 or 10,000 for a hydrogen system. Yeah, it's not. I don't want to say £5 notice. It's a lot of money, not a massive percentage on the boat, and we can expect those costs to come down with time.
Okay, thank you, Bowman. So we'll hand across to Juan now, who's going to give the second presentation on Kite wind turbines. Over to you, Juan.
Thank you, Andy. Good evening, everyone. Thank you for joining us today in this short technical talk. Since we have some issues with the quality of audio and video, so I'll keep my camera turned off, if that's okay, just saving the bandwidth. Okay, so I suppose it's quite apt that the topic today reaches on sustainability, and that we're all doing this the most that we can by staying inside on this Earth Day. So happy Earth Day. Thought it could be beneficial to host an event like this for people who are interested in perhaps learning about something new. So this won't be an in-depth discussion on this topic or this technology, rather a brief introduction to this emerging technology to harness wind energy. So a quick introduction about myself. My name is Djawad. I'm the chair of the Young Members Panel here in Teesside. I was previously a panel member of IMechE in Malaysia. We've actually broached the same topic. I can see some participants they're dialing in from Malaysia, so you guys will be well past midnight now, so thank you for staying up. I currently work for a company called IMechE, based in Darlington, in the northeast of England. Our core business involves supporting the infrastructure of, among others, renewable energy sector, having developed structures to support the installation of offshore wind farms as well as involvement in midstream segment of the renewable energy industry. So I'm quite interested in wind turbines in general. So I'm not an expert in particular technology, by the way. It's just simply a topic that I'm interested in, especially with through my work with IMechE. So we have designed structures for offshore deployment, including those involving the installation of offshore wind turbine. I first came across a company called IMechE back in 2011. I'll speak more about them in a bit. When I first presented the same topic at an IMechE event as well. At the time, the initiative to develop the Kite wind turbine at a commercial level was in its infancy. So I thought it might be a great idea to introduce this to even more people now that there are been some developments in terms of funding and technology to make this commercially viable. So Kite, right, I'm going to give you a brief history of Kite. Kite's been around for over 1,000 years. The Chinese, I believe, use them for military applications and even for lifting man. So they knew at that stage that it could carry large weights. I'm not sure why there is a hole in this man though. In 1827, a fellow named George Pocock was an English school teacher. He was quite a prolific inventor as well. Was very interested in developing systems to kind of pull loads using kites, and eventually pioneered the use of kites for towing buggies in races against horse carriages across the English countryside. So in that little picture there, this was the buggy called the Charvelant, and it has a kite tethered to it. You can see this little black blotch there, and it could actually go fast enough for it to race against horses. And of course, at the dawn of aviation, all of the great inventors of the time, like Hargreaves, Samuel Langley, like even Alexander Graham Bell, the inventor of the telephone, were flying kites in the pursuit of aviation. And then these two fellows came along, and they were flying kites to develop a control system that would ultimately enable powered human flight. So, of course, they were Orville and Wilbur Wright, and the Wright flyer and their experiments with kites led to this momentous occasion where they powered up and took off for the first ever 12-second human flight in 1903, and we all know about that. And that was fantastic for the future of commercial aviation, but unfortunately it relegated kites once again to be considered children's toys. So that was until 1970s when we had our last energy crisis. Funny that today oil prices in the US are in the red for a completely different reason. So this man named Miles Lloyd, who lived in the outskirts of San Francisco, wrote this seminal paper that was completely ignored in the Journal of Energy about how to use basically an airplane on a piece of string to generate an enormous amount of energy. So the real observation he made was that a free-flying kite can sweep through more sky, and more sky equals to more power in a unit of time than a thick wind turbine. So how does it work? It's quite simple, really. The kite is tethered to a dynamo, almost, or a ground energy generator, or an alternator, through a string. The string then rotates the alternator as the kite rises and descends. So more likely it's a steel cable. And that's basically how, in principle, the kite generates electricity. So turbines grew, and they can now span up to 800 feet, I believe, at the hub height. But it's really hard to go up much higher, and more height is where more wind is, and more wind would generate more power, as much as twice as much. And there are plans to develop larger wind turbines. As you probably know, if you're a bit of a turbine enthusiast, GE is investing to develop the world's largest offshore wind turbine, a 12 megawatt, I think it's 260 meter height, of the Heliad X. So the current Vestas wind turbine, Vestas 164, at 220 meters can produce 8 megawatt of energy. So cut to now, we still have an energy crisis, and now we have a climate crisis as well. So humans generate about 12 trillion watts or 12 terawatts from fossil fuels. Now, Gore has spoken about why we need to hit one of these targets, and in reality, what that means is that in the next 20, 30 years, we have to make about 10 trillion watts more of new clean energy somehow. Wind is the second largest renewable resource after solar, 3,600 terawatts, more than enough to supply the energy for the human race 100 times over. The majority of it is, however, in a higher altitude, where we are not yet capitalizing on a large scale. So just something to think about. Towards the end, why is it that the higher potential for wind energy can only be found higher up, thousands of feet, and not much closer to ground, which is what this whole technology is aiming to achieve? So a company called Makani back in 2010, 2011 tested a prototype on the island of Maui. So I stole this screenshot here from their website showing how much energy you can get. So this is what we're looking at, working towards megawatt scale machine that can fly at 2,000 feet and produce tons of clean energy. So how big are these machines? So these representations of wingspans from airplanes. So a Cessna would be enough to produce 230 kilowatt. Take a Gulfstream, rip its wings out, and you can produce 1.3 megawatt. 747, 68.5 meter, about 70 meter wingspan. That'll give you about 6 megawatt. And the massive Spruce Goose would be a 15 megawatt wing. So compare this to the largest wind turbine by Vestas, for example, just off the west coast of UK at Burbank, with a rotor diameter of 164 meters, weighing over 100 tons. Just the wings alone produces 10 megawatts, and that's a world record over the period of 1 day, essentially 9.5 megawatts, back in 2017. So they set the world record then. They have announced the first double-digit offshore wind turbine, the Vestas 164 10 megawatts, but that will not be available for commercial installation until 2021, I believe. So let's look at some costs of the Kite turbines. Yes, so this is from another company called Kite. So there's quite a few players around. A lot of them are getting noticed and getting fundings. So the initial technology from Kite cost about $750,000, with a 100-meter wing that can produce half a gigawatt of energy at a cost of only 1.5 euros per megawatt. So that's about 30 times cheaper than average cost in Europe. So a 2016 study by the International Renewable Energy Agency published that the cost per megawatt hour of energy generated by offshore wind alone is about $170 per megawatt, expected to drop to 95 by 2030. In comparison with a Kite wind turbine, obviously it's all quite theoretical because it's not out commercially yet. But at the time, it costs $62.50, and that can reduce to $50 by 2030. So also another thing to think about, now that you've got a bit of an idea of how this wind kite works. You see at my initial slide, the very first page, it's basically like a big plane or a kite that is self-powered. It can fly itself. Why would that sort of system be significantly cheaper than a conventional wind turbine? I'll go into that at the end. We have a prototype installed for 500 kilowatt, I believe, in the southwest of England. I think that's off the coast of Liverpool. They've installed a prototype, 2 kites, 60 meters span. Sorry, yeah, it can't be southwest of England, Liverpool then. Well, 2 kites, 60 meters span. Equivalent wind turbine would be a wind turbine with a diameter of 54 meters. Would have to be really structurally strong due to the wind load, bending moment caused by the wind load, rotational motion of the turbine blades and all that, which is why in terms of structure, it would be a lot cheaper to fabricate, install, and operate a wind kite system. There is another company, I believe if I go to the next slide, yeah, so that's KiteGen, just to kind of give you an idea of how much more space you can cover with wind kites as compared to a traditional conventional wind turbine. So yeah, over here you can see that you can produce 20 tons of materials per megawatt compared to 96 tons for other conventional forms of wind power. It's in carbon. That's the space. You only need 5 kilometers square compared to 40 kilometers square. The same energy production requires only 12 kites instead of 150 wind turbines. So these are some of the players I've mentioned. KiteGen, the British company that's doing quite well now, Kite Power Systems, and Makani, which I initially mentioned. So I don't have any more slides to show of these guys. Quite last minute this, but I would like to speak about the systems that they have, all the different types. So for example, Kite Power System, the company, they use 2 kites actually tethered to a spool, like what I mentioned just now. And the way that it works is that these 2 kites tethered to a spool, they then fly in a figure-8 motion and unwinds the spool as they go. So this powers the generator, but also feeds the hydraulic accumulator that stores potential energy in the form of pressure that can be released to drive the generator to smoothen out variances in the kite. So what they're really doing here is trying to come up with a control system that could ensure sustained, consistent energy output through consistent and most optimized flight path for these kites, because this is quite significant to comply to the requirements of the energy grid, the main grid. So these kites have their own control system that provides a flight path. It has an onboard control system that will ensure the most optimistic flight. So the hydraulic accumulator is now releasing energy during uncertain wind helps ensure consistent energy output to make the system compliant with the grid's needs. So these two kites are used where one flies upwards whilst the other lowers, with a small amount of energy from the kite raising being used to re-spool the kite descending. So there's another question here. So when you have two kites, one going up, one going down, won't the kites then come to an equilibrium and just get stuck at some point? That's something else to think about. Like I said, they're not powered. They don't have an engine or anything like that. They get pushed and pulled, I think, by the spool, and yet they can go for hours and hours and consistently for hundreds of hours. So the other player, Makani, which is a US company acquired by Google in 2013, they are no longer, however, owned by the parent company Alphabet. However, they use a slightly different system, and they are the one from my first slide here. Just there, over there. That is the largest one that they've managed to launch in 2018. So this system here, if you can see those little rotor blades, there are 8 of them, 2, 4, 6, 8, and those blades are actually the ones turning during flight through crosswind as the kite, which is tethered, as you can see there. This is just the one kite. It flies in also a figure-8 motion, and as it cuts across crosswind, the wind rotates the turbine blades, and that generates the power. It actually generates it on board, and it transfers the electricity through that cable there back to its ground station. So that is the other system. So I think I've come to the end of basically my introduction on this. So if you have any more questions, I do have more things to share. But yeah, hopefully we have learned something from that. And if you have any question, if not, I could get back to some of the questions I've posed, and we can discuss on the principles of it. Thank you.
Okay, thanks Juan. First question we've got is, are kites good in all wind conditions, or are they mainly suitable for lighter winds, if you know that?
No, yeah. So absolutely. The very reason why this is appealing to a lot of large companies that are funding this, including Shell and Schlumberger, is because they could. So for a conventional wind turbine, obviously you're quite limited to a certain wind speed before. I think we've all seen some videos of wind turbines just flying off because of severe storm. But the kites, they thrive in extremely high turbulent winds. So the way that they move, because it's tethered, I mean, as far as the tensile strength of that cable allows them, the kites won't have any issue as long as they're tethered, because they fly following the motion of wind, and the onboard system compensates for any irregularities in the wind, I suppose, motion, if it's quite, crosswind and all that. So especially with this system here that you're looking at the screen right now, that benefits from crosswind. So it's definitely not an issue to a certain extent.
Okay, thanks, Juan. There's a couple of questions around the theme of the wind strength, and if wind strength drops off, what happens to the kite, and how do you get it back to its parking position?
Brilliant. So again, I'll use this example here. Like I said, they are controlled by an onboard computer. So this one here it actually launches itself, so you don't need to pull it, or it doesn't need a runway or anything like that. It hovers like a drone. So initially, power is fed into the kite to turn the rotors, and it lifts off and gets up to height, and then the wind takes over and it starts flying around and generating electricity. And when the wind speed drops to a level where it is no longer optimized to fly and generate electricity, it just hovers back down and parks itself. So they've done multiple trials offshore and onshore as well. If you would look on YouTube, actually, from this company, IMechE, you'll actually see that it's parked just like that, kind of vertically upwards, and it launches itself up, takes itself up to tension, and then the spool starts playing in and out, and it flies around in the loop motion. And when it's done, it flies back down, and it hovers back into place. It's quite brilliant, really.
Okay, thanks, Juan. So the final question, I think. What altitude do they fly at? What's the kind of optimum altitude? And are there any safety issues with respect to other forms of aviation?
Yes, so those are definitely serious concerns when you're talking about shared airspace. So the IMechE system goes up to 2,000 feet, but they're planning to go much higher than that. But however, there isn't any commercially viable system out there just yet. So I suppose the sky is the limit. Is the limit, quite literally. In terms of the concerns with aviation, airspace, the way that they've done the prototypes and all this before is by acquiring an airspace that has been closed off. So I would imagine that in the future, if this were to become commercially available, then airspace would have to be designated as a no-fly zone, essentially. So again, like I said, there's quite some big powers at play that are quite serious in making this commercially viable. So I'm sure those are the kind of concerns that they are looking at.
Okay, I'll just do a couple of very quick final questions, Juan. Someone's asked if you knew what the lifespan is for a typical design. And someone else was asked if you know how noisy they are when they operate.
I am not sure, actually. In terms of how noisy they are, yes, I understand that question, because wind turbines generally is an issue because they're quite noisy. But these kites, they're really, because they're quite high up, noise isn't really an issue. So that's not something that have been raised as an issue by some of these companies, at least. So no, I wouldn't say that is the main concern. The main concern would most likely be the no-fly zone issue. And in terms of lifespan, I'm not sure. No, I'd have to kind of look more into that, because again, like I said, they've not been commercially available just yet. But yeah.
Okay, well, thank you for that one. That was interesting, giving a bit of an overview, bit of an introduction to the technology.
Mm-hmm.
So we'll bring tonight's webinar to a close. Thank you to Juan and Bowman for their presentations. Thank you to Emma from IMechE HQ for helping us get things set up. And as I said at the start, if you're interested in getting involved and helping us give a technical talk in the future, please get in contact with myself via the Near You page on the IMechE website. Okay, thanks very much and good night.